Now next result is every closed subsequence of normed linear space is weakly closed. So that is every closed subspace of norm space is a weakly closed. Suppose M is a closed subspace of N. So we want to prove that M is weakly closed. If we want to show that M is weakly closed, so we take a some weak limit of M, then prove that that limit belongs to this set M. That prove our result. Let P be a weak limit of M. First step, let P be a weak limit of M. By definition, there exists a sequence Pn in M such that Pn weakly convergent to P. Then by definition of weak convergence, limit n approaches in infinity f of Pn, which is equal to f of P for every f belongs to n star. N star means dual space. Now, our purpose is to show that P belongs to M. That is our purpose. We assume P does not belongs to M. If we assume P does not belongs to M, by existence of functional theorem, there exists a G belongs to N star. G is some functional. So this is a corollary, the next part of Hahn-Banach theorem, that is called existence of functional theorem. So remember that result, otherwise see in the book. By existence of functional theorem, so this is a next theorem of Hahn-Banach theorems. By existence of functional theorem, there exists a G belongs to N star such that norm of G equal to 1 and G of P is equal to D. So what is D? D is a distance of P from M. It means P does not belongs to M. So it means distance of P from M is non-zero because both the P does not belongs to M and other points belongs to M. So distance between P M is non-zero. So it means GP is equal to not equal to 0. Remember this result. Now it implies G of Pn equal to 0 for every n belongs to 2, 1, 2, 3 since Pn belongs to M. So Pn belongs to M. So it implies G of Pn approaches to 0. Gp is non-zero. Gpn is 0. So it means Gpn does not converge to Gp because one term is this sequence is 0. Why 0? Because Pn belongs to M and Pn belongs to M means distance between these values 0 and P does not belongs to M, so distance is non-zero. So it means Gpn does not approaches to Gp, which contradicts the hypothesis of weak convergence. So in weak convergence, it should be for every functional G of Pn approaches to G of P. But here it does not approaches to Gp, which contradicts the hypothesis of weak convergent of Pn. So it means that we assume is not right. So what we assume P does not belongs to M. It means which is a contradiction. Our supposition is wrong. So it means P belongs to M. If P belongs to M, then M is a weakly closed. So that prove this result. Now, convergence of sequence in case of operators. Now, if we take N is norm space, N dash is norm space, already we know that Bn to n dash, it is a set of all bounded linear operator from n to n dash. Let Tn belongs to B and n dash. It means Tn is a sequence of bounded linear operator. Then here we have three definitions. So remember that definition. If Tn uniformly convergent to T, suppose Tn is some sequence which is a uniformly convergent to T, if and only if norm of Tn minus T approaches to 0 as n approaches to infinity. So this is a definition of uniform convergent. Similarly, Tn approaches to T if strongly convergent. S means strongly convergent. If Tn strongly convergent to T, in that case, norm of Tnx minus Tx approaches to 0 for every x belongs to n. Third is Tn is weakly convergent to T. In that case, norm of f of Tnx minus f of Tx approaches to 0. So this f is a belongs to n star. N star is a dual space of n. Yeah, f is a bounded linear functional and x belongs to n. So x is a sum vector. So this is when n approaches to infinity. So compare these three definitions. One is uniform convergent, second is strongly convergent, and third is weakly convergent. So first Tn minus T, here Tnx minus Tx. Now here f of Tnx minus f of Tx, this norm approaches to 0. Now we know that every uniform convergent implies strongly convergent. Strongly convergent implies weakly convergent, but converse is not true. Converse is not true. So first part, uniform convergent implies strongly convergent. Let a sequence Tn, which is a uniformly convergent to T, then by definition, that is in written in equation number 1. Now, norm of Tnx minus Tx for every x belongs to n. This can be written as in this form. Now, this is a bounded operator. So by definition of bounded operator, Tn is bounded, T is bounded. So Tn minus T is bounded operator. Now by definition of bounded operator, this is less than equal to norm of Tn minus T into norm of x. Now by equation number 1, this term approaches to 0. If this term approaches to 0, then right hand side of this equation is again approaches to 0. If right hand side of this equation is approaches to 0, it means limit n approaches infinity, norm of Tnx minus Tx is equal to 0 for every x belongs to n. Then by definition, this sequence is strongly convergent to T. This sequence Tn is strongly convergent to T. But converse is not true. That we discuss later on. Number 2. Every strongly convergent sequence are weak convergent. For example, let Tn is strongly convergent to T, then by definition, Tnx approaches to Tx as n approaches to infinity for every x belongs to n. Our purpose is to prove this result, basically ftnx. So basically it does not implies. So we want to prove that f of t and x. Huh. Now, why it implies f of t and x approaches to f of tx? Now this f belongs to n star. If f belongs to n star, then f is a bounded linear function. If f is bounded linear function, bounded and continuous, these are the same thing in function analysis. So f is a continuous function. By definition of continuity, if a sequence is convergent to its limit, then its image is again convergent to its image. So by definition of by continuity, that we discuss in real analysis. If Tnx approaches to Tx, then f of Tnx approaches to f of Tx. This is possible because f is a continuous transformation. Then it implies norm of ftnx minus f of tx approaches to 0 as n approaches infinity. This is for every f belongs to n star. Then Tn is weakly convergent to T. So this is our result. Now, strongly convergent does not implies uniform convergence. Yani first, the converse of first part is also not true. And similarly, weakly convergent does not imply strongly convergent operator. So in order to prove this result, we have example number 1, that is page number 18 in the book. So you can see that result. Similarly, example number 2, page number 18, again you can see in the book and solve the result. So do it yourself.